Number 10. Okay, cool. Yeah, so identifying symmetries. So whenever you're doing symmetries, just grab my notes here. There's some specific formulas for it. And I think all I did was just kind of briefly mention them in the video. But there's like a nice concise list to them. So it wants to know all of the different symmetries here, and the first symmetry it wants to know about is the x-axis symmetry. So from the video or from the book, you can just kind of look it up. For polar equations, something is symmetric to the x-axis is that if you have just a generic point r theta on the graph, then you also automatically get r negative theta and or the point negative r pi minus theta. Usually it's just the first one here that you kind of worry about. The second one's kind of obnoxious. So basically what you want to look at is that if you plug in for this part negative theta in for positive theta, you want it to all stay the same. So what this is saying is that if you have a generic point on the graph, this point is also on the graph. Can we plug in negative theta and everything stays the same? So let's just do it, right? In our equation, r equals 9 plus 9 cosine. Instead of plugging just a normal theta into this, we're going to plug a negative theta into this. All right. And then inside of cosines and sines, whenever you have a negative angle, we have these properties for it. So if you still have that trig identity sheet that I gave you in the past, that would work. Otherwise, you just look up negative angle identities. They should be pretty easy to find. So here you go. So if you have a negative angle inside of cosine, this says it's the same thing as just cosine of the positive. So going back to our thing, all we would do here is just basically make that negative go away. And we get what we want, right? So if I do plug a negative theta into this, it's the same thing as just plugging a positive theta into this. In other words, this graph is going to be symmetric to the x-axis. Oh no, what happened? Oh, because I'm reviewing it like goofed up. Let me get to it a different way. Just give me a second here. I'm just pulling back up that homework, but I have to pull it up a different way so that it will actually let me work through it. I hope it doesn't change the question too much. Oh, good. It's the same thing, right? So r equals 9 plus 9 cosine theta. We just decided, yes, this is symmetric to the x-axis. Okay, to see if it's symmetric to the y-axis, again, there's just like a nice little formula or process to it. For something to be symmetric to the y-axis, if r theta is in the graph, then we also have, for the y-axis, two different ones. Either negative r negative theta has to work, and or the other one is r pi minus theta. So you could try either one of these because they really are the same thing. So if we just go back to our formula here, the r equals 9 plus 9 cosine theta, if I do substitute r to be negative r, and I substitute theta to be negative theta, the same thing's going to happen with the cosine of negative theta. It's going to stay positive, but there's nothing that's going to happen to that r value that's out in front here. So because of this negative r, this does not match the function that we started with anymore. So if I do substitute in this point, it is not a reflection over the y-axis, so it is not symmetric to the y-axis. And then the last one here, they want to know if it's symmetric to the origin. And again, there's just kind of a formula or process to it. If you have a generic point r theta on the graph, then we also have, for symmetric to the origin, it's negative r positive theta. That point has to be on the same thing, or it also has to work. But as we just saw, if I do substitute r to be a negative r, there's no way that this is going to come back to be the same thing. So it's impossible to make this look like the original function, so it's not symmetric to the origin either. The last thing they want you to do is to identify the graph, and it's kind of hard to do that. I think you can do it pretty easily for this one, just based on the A, B, C, and D, and what you have. But remember that your calculator can graph these pretty easily. Just change your calculator over to polar mode and type it in and graph it. If I had to guess, I think it's this one here that is going to be right. This one is symmetric to the x-axis, not symmetric to the y or the origin. And if I plug in 0 in for the angle cosine, I get positive 9, which makes it go like way out. Or sorry, you get 18, which makes it go way out here to 18. So it's got to be that one. Okay, cool. So does that make sense? Does that answer your question for that one, Josh? Okay, cool. Yeah, so when you do go to take the Chapter 11 test and even the final exam, make sure you have these somewhere in front of you. I would not expect you to have these memorized. This is something that you would just want to have next to you and kind of like a formula sheet to look up. In fact, I think I might have a formula sheet here for some Chapter 11 stuff. Let me look to see if I do. Yeah, if it's sine of theta and you have the negative on the inside, then the negative gets pulled out to the front and it messes some stuff up. What was I looking for? Formula sheet, that's what I was looking for. Oh, let's see what this is. It's got a lot of stuff up there, but it doesn't have the symmetries. I think that was just because on the exam I gave last time, it didn't have these on there. But of course, you guys are going to have stuff definitely on the Chapter 11 test. So just make sure you have this in front of you so that you know when to use it for these symmetries. Questions? Okay, so was there any other specific questions from the homeworks? Okay. Okay, so I think what I want to do is I'm just going to open up this final exam practice, and then for the next, I don't know how long we're going to work through it, but if you notice, right, there's 73 questions in this thing. Questions from every single chapter that we've done. For today, just because we're trying to get ready for the Chapter 11 test more than anything else, let's go through this, but only the questions that are coming out of Chapter 11. And then if we just go through all those, we'll probably just kind of head out after that. But this will be good practice for the stuff that you're going to see on the test coming up this Monday. So here we go. Just working through these. First question, find the length of the curve. The line segment r equals 7 secant theta, where theta is going from 0 to pi over 4. Okay, you don't have to graph these when you're finding the length of the curve, because they're always going to give you the bounds of your integral. What you would need, and something that you would hopefully have, again, in front of you in kind of like an organized formula sheet, is that you would need to know the arc length formula. And this is going to be the arc length formula for a polar equation. You also have the arc length formula for parametric equations as well. So just make sure you know when to use which one. This one is a polar equation because you have r's and thetas. It would be a parametric equation if you have x equals something and y equals something separately. Okay, so just looking up the formula for the arc length, and I don't have it here in front of me, so let me just find it real quick. Area stuff, length stuff, here we go. So it is this, the integral from alpha to beta. So these are just the lower and upper limits of the angle. Okay, and then the integral that you want to do is the square root of r squared plus dr d theta squared, d theta. Okay, and again, like I would not expect you to have this formula memorized. It's just the formula for the arc length given a polar equation. So now let's take the equation that we have and let's plug it into this and do the integral. So for us, we're going to have the integral, and it tells us the limits. All right, so our limits are going from 0 to pi over 4. And then plugging in my r, we're going to have r squared, so that's going to be 7 secant of theta all squared, plus, so then the derivative of r with respect to theta, the derivative of secant is secant tangent. Cool. So 7 secant theta is going to change into 7 secant theta tangent theta, and then that is all squared. And then we still have a d theta on the outside. So this integral is not fun. It's not going to be super easy, but we should be able to do it. So let's just see how it's going to work. So simplifying this down, this is going to change. Still the integral from 0 to pi over 4. We'll square off all that stuff on the inside of the square root here. So 7 secant squared is going to change into 49 secant squared. Plus, and the other one would just change into 49 secant squared tangent squared. And there's not too much that we can do with this as far as trig identities go. But what I'm noticing is that both of these terms have a 49 secant squared in it. So I'm going to factor that out. And in fact, I'm going to factor it all the way out of the square root here. So this is still going to be the integral from 0 to pi over 4. Now I'm factoring out 49 secant squared from each of the terms, but that's a perfect square, so that'll come out of the square root as just 7 secant of theta. Still do have the square root, and now inside the square root we just have what's left over after factoring out that 49 secant squared, which is going to be 1 plus tangent squared. All right, at this point, I would start thinking of u substitutions and how we could do that, but it doesn't look like it's going to work out yet. Like if I let u be the inside of the square root, the derivative of tangent squared would be something kind of crazy. It's definitely not just 7 secant of theta. So we're going to have to keep trying some different things until we can break this down. The next thing that I'm noticing is that 1 plus tangent squared, I'm pretty sure is one of the Pythagorean identities that we have on our trig identity sheet. I think 1 plus tangent squared is just secant squared. So now my integral, still going from 0 to pi over 4, still have that 7 secant theta out in front, but now inside the square root, I'm almost certain 1 plus tangent squared is going to change into secant squared. And now we're taking the square root of secant squared, which is just secant, and then I can multiply that onto this other secant. So now my the thing I'm trying to find the antiderivative to is 7 secant squared. All right, and at this point, hopefully you still have that table of integrals that I gave you, or if you're very comfortable with the trig functions and their derivatives and their antiderivatives, this one shouldn't be too hard to find and think about. What you're looking for is a function that when you do take the derivative, you get secant squared, and that function is tangent. So the antiderivative of this is going to be 7 tangent of theta. And again, that's because if I took the derivative of 7 tangent, it would give me back to 7 secant squared. And then that we're going to evaluate from 0 to pi over 4. So if I plug pi over 4 in for tangent, tangent of pi over 4 is just 1. So we just get 7. Minus, if I plug 0 in for tangent, I get 0. So my answer should just be 7. Going back to the homeworks, let's see if 7 is any of the answer. And yeah, it looks like this first one here. Okay. So I know that that integral was a little bit difficult, but just playing around with it, using some trig identities, factoring stuff out, it wasn't too bad. But is that one all right? Any questions about number 73 on this practice final thing? Cool. All right, let's try the next one. 72. Okay, so here, find the area of the specified region inside one loop of this, the r squared equals 3 cosine 2 theta. And I think we did one like this last time on the other thing. We'll just go through this one real quick. The hard part here is going to be graphing this thing. So you are going to want to take the square root, which is going to end up being both a positive and a negative square root. But I think we figured out last time that we don't even need the negative square root, because we're just trying to find the area inside one of the loops, and it's symmetric on both sides. So it doesn't matter if we do the positive or the negative. The next thing that we had figured out when we were graphing this is that it turns out the angle theta only needs to go from 0 to pi over 2 for it to circle around the loop just once. So that's just playing around with the lower and the upper limit in the calculator for theta to see what's going to generate just one loop of this shape. Okay, and then you just do it. So after that, you do need to find the area formula for polar. And it is a formula to it. Do not just integrate over this, because you're going to get the wrong answer. In polar form, it's the integral of 1/2 r squared d theta. Okay, so plugging in the stuff that we have, we're going to do the integral from 0 to pi over 2 of 1/2. And then my r is this square root thing, and we're going to square it. So let's just write it out for now. So my r is going to be the square root of 3 cosine of 2 theta. Cool. And then a d theta on the end. All right, so if we square that, that's just going to make the square root go away. Still going to have the integral from 0 to pi over 2. You could pull the 1/2 out, but you're also going to be multiplying this by a 3. So we're going to have a 3/2 out in front, and then a cosine of 2 theta. And now we can just do the antiderivative. So the antiderivative of this, we still have the 3/2 out in front, but then we're going to divide by another 2 to make it a 3/4. And then the antiderivative of cosine is positive sine. So we're going to have 3/4 sine of 2 theta. And then that antiderivative we're going to evaluate from 0 to pi over 2. Whoop, did not want to do that. There we go. All right, so if we plug pi over 2 into this, 2 times pi over 2 is just pi, and sine of pi is 0, so we just get 0. Minus, plugging 0 into this one, we also get 0. Did I goof somewhere? Did I write something down wrong? I think I messed this one up the last time I did it too. Maybe it's our limits going from 0 to pi over 2. Yeah, it must be the limits that I've goofed up. All right, let me go into Desmos and really graph this thing out. So square root 3 cosine 2 theta. R equals square root 3 cosine of 2 theta. Cool. So we were trying to do 0 to pi over 2. Oh yeah, look, so that's not even one full loop. That's why it wasn't working out. Let's try going from 0 to pi. That's still not even like a full loop. That's some weird thing. Maybe we have to start somewhere else. Instead of starting at 0, let's try starting at negative pi over 2 and going to positive pi over 2. All right, so if I do that, negative pi over 2 to positive pi over 2, that gives me like a full loop. All right, so let's go back to my thing and let's change my limits. Although it still looks like it's going to be weird. I think that's still going to give me 0, and it's going to give me 0 because of the negative and the positive adding up. So we gotta be more clever. What if we did pi over 4 to pi, or pi over 4 to 3 pi over 4? Oh, I didn't even like that. I didn't do anything. Well, we could just do that and cut it in half. Just go 0 to 2 pi and cut it in half. That might work. I think that would still give me zeros everywhere though, because the areas would end up like canceling each other out. Oh no, I'm at a loss. That one might work. Pi over 4 to 5 pi over 4. That gives me this the other loop. Let's try that one. Pi over 4 to 5 pi over 4. So if I plug 5 pi over 4 into this, that's going to be sine of 5 pi over 2, which I think is negative 1. So we're going to end up getting negative 3/4. But then the other one is going to be minus sine of pi over 2, which is positive 1. So minus another 3/4, which gives us 6/4 or 3 halves. But it can't be minus, so it has to be the positive. I know that was kind of a cheating way of getting the right answer there, because our limits are still like goofed up. But it's just because it's such a weird shape to it that it's difficult to figure out what the limits are really supposed to be. What was that? 5 pi over 2 is the same thing as pi over 2. I guess it would be, wouldn't it? Yeah, you're right, it would. So we would still get 0 if we did it that way. Oh no, I did. Oh man. Crud. You're right, George. Alright, let's really dive into this. So another thing that we can think of is that we can think about the period of the function. Because when you throw a 2 inside of the cosine, it changes the period. The period of this is no longer 2 pi, the period is just going to be pi. which means that it should repeat every pi units. So if I go pi over 4 and then the next one over 5 pi over 4, that should get me back to, like I was saying before, like one loop of the function until it starts repeating. Okay, but when I tried that, which is what I just did, I still get 0, right? And I think we're getting 0 again because the areas top and bottom are canceling each other out. I guess what we could do is that we could just do pi over 4 to 3 pi over 4. Or what was another one? 0 to 3 pi over 4. That might work. So this is just half of a loop. We can find the area of a half of a loop and then just double it. So going from 0 to 3 pi over 4 instead. If I plug 3 pi over 4 into that, that's 3 pi over 2. It still gives me a negative, which sucks, but it does. But that's the area of half of a loop, and then you can double it to find the area of a full loop. All right, anyway, there we go. I do want to also say that your calculator can do integrals as well with these. So when you go to that integral function, you just plug in the limits of the theta, and it should kind of map it out for you. Okay, so I know that these are difficult with these weird shapes. I made sure on the test that you don't have any of these weird shapes. The majority of the ones that you're going to see are going to be nice ones. Well, look, this one's another kind of awful one too. Find the area of the specified region. Another one of these things. So it's going to be a similar kind of thing. I think it's this answer just looking at it. Oh no, must be this one. Yeah. So it's kind of just whatever the number is out in front for these. I can't graph it in Desmos without plugging in a value for the A, but it's the same exact example that we just did. It's just a sine instead of a cosine on the inside. So your antiderivative is going to have a cosine 2 theta instead for here. But we'll skip this one too, because like I said, you're not going to have ones that have these awful shapes where it's very difficult to find the limits. Okay, so let's backtrack and let's start working on some other stuff. All right, so here's one that we haven't done in quite a while. This one's asking us to find the length of the curve where it's in parametric form. So what we would have to do, same thing as before, is that we'd have to find the arc length formula, but this time not for polar, for parametric. So we would go in our notes, or hopefully you have like a little formula thing all kind of mapped out. For the arc length for parametric equations, it's the integral for the endpoints of the parameter. You still have a square root in there. And inside the square root is going to be the derivative of the first parameter with respect to, the derivative of the first function with respect to the parameter squared, plus the derivative of the second function with respect to the parameter squared. And then outside the square root, you have the dt. All right, so this is just the formula for the arc length when you have parameterizations. All right, so just plugging in what we have into this. We still are going to have the integral, and it says specifically that our limits are going from 0 to 4 for the parameter. Square root. The derivative of x with respect to t is going to be a little awful looking, but hopefully not too bad. It might even be easier to distribute the 1/3 into there, but I guess you don't have to. So this thing, the derivative, I'll just leave the 1/3 out in front. Then the derivative of t cubed is 3t squared, minus the derivative of 3t is just 3. All right, so it's going to be that whole thing squared, plus the derivative of the y, which is just 2t squared, and then dt on the outside. Okay, cleaning this up. It's still going to be the integral from 0 to 4. Inside the square root now, simplifying all that stuff down, When we square this out, we can just square each of these terms separately. 1/3 squared is 1/9, and then that 3t squared minus 3, that we would have to FOIL all out. So let's go ahead and FOIL that. Pretend there's two of these binomials side by side. We're going to have 3t squared times another 3t squared, which is 9t to the 4th. The inner and the outer is going to be negative 9t squared, but there's two of them, so negative 18t squared. And then we're going to have a negative 3 times negative 3, which is a positive 9. Okay, so that's still to the x one. And then just squaring off my y one here, 2t all squared would be 4t squared. Okay, now we'll distribute out the 1/9 into here, and then we'll combine like terms to see what we can get. So this will be the integral from 0 to 4 still the square root, but inside the square root, 1/9 times all of this just divides everything by 9. So we're going to end up with a t to the 4th out in front. This is a negative 2t squared that's adding on to a 4t squared, so positive 2t squared, and then we have the plus 1 from this 9 times 1/9 out here. Okay. As it stands now, that is not something that we can do just as is. There's no u substitution to it, so we can't do that. After u substitution, the next thing that you want to try is either completing the square, which you can do for these, or if it's already a perfect square, then just factor it. And this turns out to already be a perfect square. So this would just be the integral from 0 to 4 of the square root, and when I factor the inside, that would factor into t squared plus 1 all squared. Okay, so just factoring the trinomial on the inside. The square root and the squared cancel each other out, so we still have the integral from 0 to 4. Where did the y? Oh, I combined it. So there was this 4t squared out here, but this ended up being a negative 2t squared from the 1/9 and the negative 18. So the negative 2 and the positive 4 is a positive 2t squared here. All right, so canceling out the square root and the squared, we just end up with the t squared plus 1. That we can find the antiderivative for. That's going to be 1/3 t cubed plus t. That we're evaluating from 0 to 4. If we plug 4 into this, 4 cubed is 64, I think. So it's 64 thirds plus 4. And there's no point plugging 0 into this because we're just going to get 0. So now just combining these two things together to actually get an answer. I think that's 12 thirds, so 76 thirds overall, which is that one. Okay, cool. All right, so I mean, it's just plugging stuff into the formula for the arc length of parametric equations. All right. Good, so is that one all right? Any questions about that one? All right, let's keep going back then. So this next one is definitely one that's going to show up on the test. Find an equation for the line tangent to the curve at the point defined by the given value of t. So here we're given our parametric equations and the value of t, and we have to find the tangent line to that. So anytime you're trying to find a tangent line, that's when you're going to be using that equation of the line, the y minus y1 is equal to m times x minus x1, called the point slope form of a line. So to do this, we need to know a point, the x1, y1, and we need to know the slope m. And we don't have either one of those yet. So let's go ahead and find the slope first. Whenever you're trying to find the slope of an equation, that really means you're trying to find the derivative dy dx at the location. Because this is written in parametric form, finding dy dx is not as simple as just taking a regular derivative, but there is a formula to it. For parametric, dy dx is the same thing as dy dt divided by the derivative dx dt. So we just have to do each of these separately and then take the quotient. So dy dt, where y is 8 sine t, the derivative of 8 sine t would be 8 cosine t. And we're going to divide that by the derivative of x with respect to t. If x is sine, the derivative of that is just cosine. Okay, so now we need to evaluate the derivative at the location. In other words, we're just going to be plugging in t to be that pi over 3. So we're going to get that our derivative, our slope, I guess you can think of it, our slope m is plugging pi over 3 in for these cosines, but they do cancel, right? I hope you can just kind of see that they canceled out up here as well. So really the slope or the derivative is always just going to be 8. So we have a slope of 8. Okay. Other thing that we need to find is we need to find the point at the location. To do that, again, we're just plugging in that t equals pi over 3. But this time we are plugging it into the parametric equations instead of plugging it into the derivative. So we have to do x is equal to, this is going to be sine of pi over 3. And then y, we're going to do the same thing. That's going to be 8 sine of pi over 3. Oops. So I don't have a unit circle or a calculator in front of me, but I think this is square root of 2 over 2. I might be wrong on that.
I got square root of 3 over 2.
Oh, yeah, you're right. Square root of 3 over 2. Thank you. So then y would be 8 square root 3. Over 2. Okay, cool. So this would be my points, my x1, y1. And then just plug them in. The point slope form. We get this, right? So we're going to get y minus the y of the point, so y minus that 8 square root 3 over 2, and that's equal to the slope, which was 8, x minus the x component, square root 3 over 2. Usually you can just leave it like this and plug it in, but of course this is multiple choice stuff, so we have to keep going until it matches. We'll distribute the 8 into here, and then we'll add over the 8 root 3 over 2. And I hope you can just kind of see what it's going to do without me typing it all out. The 8 root 3 over 2 on the left is going to cancel out with the 8 root 3 over 2 on the right. We're just going to end up with y equals 8x. All right, cool. So is that one all right? Is there any questions about that one? All right, let's look at the next one. Same kind of thing here, right? So we'll just work through this one also real quick. Find the equation for the tangent line to the curve at the point given. So they give us the parametric equations and they give us the point, and we're trying to find that the tangent line. So first thing we would need is we would need to figure out the derivative dy dx. This is coming from the formula. The derivative dy dt divided by the derivative dx dt. So taking the derivative of our function y, if y is 7 cosine t, the derivative of that is negative 7 sine t. We're going to divide that by the derivative of x with respect to t. X is 7 sine t, but the derivative of that is positive 7 cosine t. Okay, so it's just simplifying this down. The 7's end up canceling each other out. This is going to be negative. and then sine t over t is tangent t. Okay. We'll plug in the location, or the parameter, whatever you want to call it. So we're plugging in 3 pi over 4 into tangent of t. And I think this is -1, but it's going to cancel out with the negative that was already there, so we're going to get a slope of +1. All right, we'll also need the point. That we'll get by plugging in the 3 pi over 4 in for the x and the y. So we're going to do 7 sine of 3 pi over 4. And we're going to be doing y is 7 cosine of 3 pi over 4. All right, so just plugging those in and getting the values for them. 3 pi over 4 into sine is positive root 2 over 2. So x is 7 root 2 over 2 for the y. Cosine at 3 pi over 4 is negative root 2 over 2. So this one's negative 7 root 2 over 2. All right, and then plugging all that into the formula, y minus y1 equal mx minus x1. That's going to be y is going to be plus the 7 root 2 over 2. And that's equal to my slope, which is just 1, x minus the point 7 root 2 over 2. All right. So the 1 doesn't do anything. We're going to end up subtracting over the 7 root 2 over 2. And then when you add these two things together, 7 root 2 over, or sorry, negative 7 root 2 over 2 and another negative 7 root 2 over 2, those are going to cancel out to just be a regular 7 root 2. All right, because you're adding them together, so you're going to add another 2 out in front, or you can think of it as being 14 over 2, which simplifies back down to be 7. So it's got to be this one, D. Okay, I think there's only one more here. Let's see, 1 or 2 more. Yeah, that's chapter 10 stuff. So just one more to look at here for the chapter 11 stuff. We'll do it real quick. Parametric equations and a parameter interval for the motion of a particle in the xy plane are given. Identify the particle's path by finding a Cartesian equation for it. Graph the Cartesian equation. Indicate the portion of the graph traced by the particle and the direction of motion. All right, so basically you're just trying to find the graph here. But it really does break it down. So let's look at breaking it down for what I could potentially ask on these homework questions. This is what you're given. You're given x equals the 4 cosine t and y equals the 4 sine t. And you're given the parameter t goes from pi to 2 pi. Okay. The first thing that they're asking you to do is they're asking you to change this to a Cartesian or rectangular equation. In other words, a regular equation that we've dealt with our entire life. There's a couple of different ways to do this. One way of doing it is to use those transition equations that we saw for the polar stuff. Another way to do it is to solve one of these for t and then plug it into the other. That one may be a little bit obnoxious because you're dealing with trig stuff, but it's still doable. So what you could do is that you could solve the x equation for t. So just doing that real quick, you would divide the 4 over and then take the cosine inverse and get that t is the cosine inverse of x over 4. But then you would be taking this and substitute that into y. And that would give you y equals 4 sine cosine inverse of x over 4. All right, and I know that looks gross. And if you took trig or 172 recently-ish, that may even look somewhat familiar in the types of problems that you saw back then. This you can fix by using some triangle stuff. Okay. I wouldn't really expect you to do it this way because it's not pertinent, and it's okay not to do it this way. Another way, of course, is just recognizing that anytime you have a cosine for the x and a sine for the y, it's going to end up being a circle. So just write down the equation of this circle, and that's what you're going to get. So this is a circle of radius 4 because it has a 4 in front of both the cosine and the sine. And then just a generic equation that has a radius of 4 for a circle would be x squared plus y squared equals the square of the radius 16. So that has to be the equation. It's also going to be centered at the origin just based on the way that the parameters are set up. There's no plus and minuses here for the x, no plus minuses here for the y. All right, so if you wanted to, you could take the time. It wouldn't be a lot of time, but just fiddle with this, and this will eventually become this, I promise. Once you have the x and the y on one side by itself. Okay, anyway, moving on. So that's the first part of it. The next part is that they actually want you to graph it. If this is a circle of radius 4, the other part of it is the parameter is going from pi to 2 pi. And you can think about that as the unit circle itself. So the pi would be over here on the left-hand side of the x-axis, and it would go from that pi over to 2 pi. So now let's look at it. It's either B or C. It all comes down to this, the direction that it's going. And again, it's just the normal direction for the unit circle, which is counterclockwise. So counterclockwise has to be the motion is going from this negative 4, 0 at pi, sweeping underneath all the way to the positive 4, 0 here at 2 pi. Okay, but I hope that kind of breaks that one down maybe a little bit more than you thought of it before when you were just working through the homeworks. But is that one all right? Is there any questions about that one? So I don't think that these are everything that you're going to see on the Chapter 11 test. So remember, there's just some stuff that I'm thinking of off the top of my head that we didn't look at today. There was these problems that were like this one, where you're trying to find the tangent line, but they took it one step further. Instead of just finding the first derivative, sometimes they asked you to find the second derivative. Other stuff that we didn't really do here, I mean, we kind of did it in this example, but we didn't do it for polar equations, is that sometimes they'll give you a polar equation like this, and then they'll ask you to change that into a Cartesian equation, or vice versa. They'll give you a Cartesian equation and ask you to change it into a polar equation. So that is using those 4 equations, these 4 equations, the x equals r cosine theta, the y equals r sine theta, the r squared is x squared plus y squared, and then the tangent of theta is equal to y over x. Just make sure you have these 4 equations with you when you go to take the Chapter 11 test, because you're going to be using them a lot. Okay, is there any last questions about the Chapter 11 test at all? Everybody feel good about it, ready for it? Okay, cool. We'll just go with everybody's good. So, awesome. Next week, of course, you have the Chapter 11 test on that Monday. But I'm going to do extra meetings next week, and we're just going to basically go through this, the practice exam. And then if you guys have any questions from the paper, that PDF file I sent you, practice exam, we can look at some of that stuff next week as well. So next week we're going to be meeting Tuesday, Wednesday, and Thursday from 11 to 12, just to kind of get ready for the final exam, which don't forget is happening next Friday. Okay, cool. All right, but that's it for today. Then, of course, if you guys have any questions as you're getting ready for the Chapter 11 test or before you take it, feel free to email me. and I'll try and write something up or make a video real quick about answering that question. Focus on the chapter 11 stuff first. If you want to take it early, of course you can take it early, and then that'll give you more time to prep for the final exam. All right, cool. So I hope to see you all Tuesday, Wednesday, and Thursday next week to get ready for the final. And of course, good luck on the chapter 11 test on Monday. But see everybody next week. Thanks for coming. I appreciate it. Hope you learned something. Have a good weekend.
You do the same.
Thanks.